Welcome, nocturnal minds, aboard. Your learning journey starts now. Having explored the foundational principles of scientific ethics and methodological rigor, we now turn our attention to a question that has captivated thinkers for millennia. What does it truly mean to explain something? While the quest for understanding dates back to ancient Greece, the modern philosophical investigation into the structure of scientific explanation really took off in the mid-20th century. The star of this show, the one who put the DN model on the map, was Carl Hempel. His work wasn't just a passing idea. It became the central battleground, sparking decades of debate and inspiring a whole zoo of alternative theories that are still being debated today. So, what exactly is this DN model Hempel championed? At its heart, it's beautifully simple, almost suspiciously so. Think of it like this. An explanation is basically a good logical argument. You have the thing you want to explain, the explandum, the mystery you're trying to solve. And then you have the explanans, the set of facts and rules that supposedly solve that mystery. The magic trick is that the explandum must logically follow from the explanans. It's a deduction, but there are two crucial ingredients. First, the premises in your argument can't just be any old statements. They need to be empirically testable and importantly true. Second, and this is the kicker, the set of premises must include at least one law of nature. This law isn't just some random fact. It has to be essential, non-redundant in the deduction. Usually, you'll also throw in some specific initial conditions, what was happening before the event you're explaining. Whether you're explaining why this specific apple fell, or why apples generally fall, the DN framework aims to capture that structure. Let's make this concrete with Hempel's own example, soap bubbles. Imagine you see bubbles forming, expanding, and then shrinking. How do you explain this? According to the DN model, you gather your facts. Maybe the temperature inside the bubble is higher than outside, the air pressure difference, the surface tension properties. Then, you bring in the laws, things like the ideal gas law, which relates pressure, volume, and temperature. If you combine these specific conditions and general laws correctly, the conclusion is that the bubbles will expand and then contract should logically follow. It's like saying, given these starting points and these universal rules, it was bound to happen this way. Simple, elegant, and seemingly powerful, until you start poking holes in it. Now, while the idea of a valid deduction seems straightforward, the real battleground quickly shifted to that second part, the law of nature. What exactly counts as a law? Is it just any statement that holds universally? Or is there something more special about laws compared to mere generalizations? Philosophers have been arguing about this for ages. Think about gravity versus the fact that all humans are mortal. Both seem like general rules, but one feels like a fundamental law of physics, the other like a contingent biological fact. Defining the difference and figuring out why laws are supposedly so important for explanation became a major headache. For anyone still clinging to the DN model, nailing down a solid definition of lawfulness wasn't just an academic exercise, it was essential for the whole enterprise to stand on its feet. Okay, so the DN model works great for deterministic laws, things like E equals mc squared, where if you know the inputs, you know the output with certainty. But what about the messy probabilistic world of statistics? Hempel, being a smart guy, realized his model needed an upgrade. Enter the IS model, inductive statistical. The core idea here is similar, but instead of guaranteeing an outcome, the laws now tell us about probabilities. Let's say there's a statistical law, exposure to measles virus gives you an 80% chance of getting measles. Now Jones gets exposed E and develops measles M. Can we explain using S and E? Yes. Because together, they show that M was highly probable. It's not a deductive certainty anymore, but an inductive leap showing likelihood. It's like saying based on the general trend and this specific case, this outcome was pretty darn likely. It's a cousin to DN, but for when things aren't perfectly predictable. So why did Hempel think explanations had to be structured like DEN or IS? He pointed to two main reasons. First, he argued that the whole point of a good explanation is to show that the phenomenon wasn't a surprise. It was expected given some underlying law and the initial conditions. It's like saying, aha, it makes sense now, because it fits within the grand scheme of natural laws. This gives us that satisfying feeling of understanding why something happened. Second, Hempel tied explanation closely to causation. He believed that whenever we talk about causes, we're implicitly talking about laws. A cause, he thought, is part of a cluster of conditions that regularly lead to an effect, according to some law. So, if you can give a causal explanation, you've essentially provided a DN or IS explanation, even if implicitly. For Hempel, causation and lawful explanation were two sides of the same coin. But then came the troublemakers. Philosophers started finding examples that just didn't fit the DN/IS mold. These counterexamples began to chip away at the foundations. Take the first one, the flagpole and its shadow. Knowing the pole's height, the sun's angle, and light laws, you can deduce the shadow lengths. Seems explanatory, right? Fine. Now, reverse it. Knowing the shadow lengths, the sun's angle, and light laws, you can deduce the pole's height. Logically valid deduction, check. But intuitively, does knowing the shadow length explain the pole's height? Most people would say no, the direction matters. That's Bromberger's famous asymmetry. Then there's Salmon's hexed salt. If you have a law, all hexed salt dissolves, and you know your salt is hexes, you can deduce it dissolved. But intuitively, the hexing is irrelevant. Whether it dissolves depends on chemistry, not magic. Finally, Scriven's syphilis case. Having latent syphilis makes paresis likely, but not guarantees, say, 100% probability. Explaining P by pointing to S doesn't fit the DN/IS pattern of high probability conferred by laws and conditions. These examples suggested something was seriously wrong. What did philosophers do when faced with these tricky cases? Many concluded that the DN/IS model, despite its elegance, was fundamentally missing something crucial. What was it? A lot of ink was spilled, suggesting it was the role of causality. The counterexamples seem to scream about causation. The flagpole asymmetry, that screams directionality, a hallmark of causation. The hexed salt problem, it highlights that a cause needs to make a difference to its effect. Hexing salt doesn't make it dissolve whether it's hexed or not, it dissolves based on its chemical nature. So, hexing isn't a real cause of dissolving, even if it's part of a logically sufficient condition. The broader lesson seemed to be just meeting the requirements of a logical deduction involving laws isn't enough. Something about the causal connection itself must be doing the explanatory work. This realization shifted the focus dramatically. Suddenly, everyone wanted to talk about causation and develop theories that could handle these kinds of nuances. William Salmon, another heavyweight in this field, initially tried to capture explanation through statistical relevance, basically looking at correlations and dependencies. But later, he too felt that wasn't quite cutting it. He developed his own alternative, the causal mechanical model, or CM. His goal was to get beyond just statistical patterns and grasp something more physical, something ontic, about causation. How did he do it? He introduced the idea of causal processes. Think of a baseball rolling across a field. That's a causal process. It can carry information or alterations, like a scuff mark, along with it continuously through space and time. Contrast this with a pseudo process like the spot of light moving around a dome caused by a searchlight. It looks like motion, but it's not transmitting anything substantial in the same way. Causal interactions happen when these processes bump into each other, like billiard balls colliding. According to Salmon, explaining an event E means tracing out the chain of these causal processes and interactions that led to it. It's about the physical transmission of influence. This CM model had some real appeal. It grounded causation in the physical world, in tangible processes and interactions. It resonated with our intuition about mechanics, where things push and pull each other, transfer energy and momentum, and everything happens locally. It felt deeply unsatisfying compared to spooky action at a distance theories. But like its predecessors, it had its own Achilles heel. Consider the hexed salt problem again, but this time viewed through Salmon's lens. Imagine a witch waving her wand over the salt, hexing it. This wand motion and the subsequent hexing could be seen as a continuous causal process. Dissolution itself involves continuous processes governed by conservation laws. So, the process from hexing to dissolving seems causal according to CM. As we know, the hexing is irrelevant. The problem is, Salmon's model focused on the physical process doesn't easily distinguish between features of a process that matter and those that don't. It seems to need something else, perhaps something like the laws or generalizations that tell us how the outcome depends on specific aspects of the process, not just that a process occurred. Alright, let's switch gears to a different approach, unificationism. This idea feels pretty intuitive, doesn't it? We often say a theory is explanatory because it brings together lots of different phenomena under one umbrella, showing they're all governed by the same deep principles. Think of Newton unifying falling apples and orbiting planets, or physicists unifying electromagnetism and the weak force. Philip Kitcher ran with this idea and developed a sophisticated model. His core concept is that successful explanation comes from using a small number of highly general argument patterns to derive a wide range of conclusions. The fewer the patterns, the more restricted they are, and the more diverse the conclusions they generate, the more unified the explanation is. Like DN, it emphasizes derivations from general principles. But how does it handle those pesky counterexamples? Kitcher argued that derivations that seem unexplanatory, like deducing pole height from shadow length, belong to less unified sets of argument patterns compared to alternative derivations that align with our intuitions. For instance, there might be a more unified pattern for deriving height from the pole's origin story, which justifies our feeling that this is a better explanation. Kitcher took this unification idea even further. He suggested that the asymmetries we observe in causation and explanation, like the flagpole example, aren't fundamental properties of the world, but rather emerge from the comparative degrees of unification achieved by different ways of organizing our knowledge. In other words, the reason we feel the pole height explains the shadow length, but not the other way around, is because the former fits into a more unified system of reasoning. Explanation and unification, for Kitcher, are the bedrock concepts. Causality, he argued, is derivative. The relationships we label as causal are simply those connections that pop up in the most unified explanatory frameworks we can construct. It's a bold claim. Causation isn't primary. It's a consequence of our best explanatory theories. Unificationism definitely has its charms. The link between explanation and bringing things together feels right. Science constantly strives for unification. Think Newton, think Salem, and Weinberg unifying forces. And successful explanations often do feel like they reveal connections and generality. However, pinning down precisely how explanation relates to unification proved tricky. One big issue is that not all forms of unification seem explanatory. Morrison pointed out that physicists use the same mathematical language, Hamiltonians, Lagrangians, to describe both mechanical systems and electrical circuits. This is a kind of unification, allowing derivations about both, but nobody thinks it provides a unified explanation of mechanics and electricity. Similarly, Silos noted that simply comparing unification levels doesn't always give us the causal judgments we expect. It suggests causality might have an independent basis. So, while the core idea of unification being key to explanation likely holds some truth, the current versions of the theory probably need some serious refinement. How? Where do we go from here? Kjergaard pointed out something interesting. All this theorizing about explanation models often misses a crucial question. What are these models actually for? Beyond just mirroring our gut feelings, what's the larger purpose? And how does explanation relate to other things we care about in science, like making predictions or controlling events? This leads to a deeper issue: how much should we trust our intuitions about what counts as a good explanation? Hempel, defending the DN model, might ask why we find the flagpole asymmetry so compelling. Maybe it's just a confused intuition, or maybe it's about practical manipulation, not pure explanation. Woodward suggested that difference: you can manipulate the shadow length by changing the pole height, but not the other way around. This difference in manipulability seems real, regardless of how we feel about the explanation direction. This suggests we need to look beyond mere intuition and consider the practical goals explanation serves. Following up on that, Woodward suggests a shift in focus. Instead of just asking if a model matches our intuitions, let's ask what kind of information does the model prioritize, and why is that information valuable? How does the information provided by, say, Salmon's causal processes relate to other things we value in science, like unifying theories or gaining control over phenomena? Is tracing causal processes the same goal as unification? Are they complementary, or do they sometimes pull us in opposite directions? Asking similar questions about the goal of unification helps us understand its place in the bigger picture of scientific inquiry. It's about connecting the dots between different epistemic values. Remember how Hempel used the DN model as a critical tool. He wielded it like a scalpel to dissect explanations, especially in fields like history and social sciences, arguing they often fell short of providing nomologically sufficient conditions. That critical edge seems to have dulled somewhat in recent decades. Much of the work now focuses on describing successful explanations rather than critiquing failures. But a good theory of explanation shouldn't just praise the good, it should also help us identify the bad and suggest how to fix it. Another big question is universality. All the models we've discussed aim to be one-size-fits-all, applicable from physics to history. But we know that explanatory practice differs wildly. Biologists often talk about discovering mechanisms, while physicists chase laws. Shouldn't our models reflect this diversity, revealing both common threads and disciplinary distinctions? Perhaps we need theories that are more sensitive to these differences. Related to the universality issue is achievability. Some models, particularly those heavily reliant on laws, might impose demands that are just unrealistic in certain fields. As many scientists and philosophers argue, biology and the social sciences likely don't operate under the same kind of lawful regularities as physics. So, models centered on laws might just not apply well there. Linking explanation models to what is actually achievable and valuable in different domains could provide useful constraints, even if some see this as mixing practical concerns with pure theory. And circling back, a recurring theme is causation. Many of the problems these models face seem to stem from relying on fuzzy or inadequate notions of causality and what makes something causally relevant. A promising path forward, then, seems clear. We need better accounts of causation, integrated directly into our theories of explanation. It's time to stop treating causation as an afterthought and tackle it head-on. Does this mean we should ditch the entire project of modeling explanation and just focus on causation? Woodworth thinks not. Even if causation is central, there's still more to explore. Causal claims themselves aren't all created equal. Explaining planetary orbits using Newtonian mechanics feels much deeper and more illuminating than simply stating the rock broke the window. Why the difference? It likely involves factors like generality, stability, and coherence with background knowledge, though not all types of these matter equally. Furthermore, is every form of why explanation ultimately causal? Some argue for geometrical explanations in physics, where phenomena are explained by appealing to the structure of spacetime itself rather than forces or energy transfers. A truly satisfying theory of explanation needs to grapple with these questions. Is causality the whole story? Or are there other dimensions to explanatory depth? Here's a fascinating twist. Despite the fact that the DN model, in its original form, has largely fallen out of favor among specialists studying explanation and causation due to those counterexamples we discussed, its core ideas, particularly the emphasis on nomological sufficiency, continue to exert a powerful influence elsewhere in philosophy. Take the ongoing debate about mental causation in the philosophy of mind. Can my decision to raise my hand, a mental state, really cause my arm to move, a physical behavior? A common approach, championed by figures like Fodor, defines causal relevance in terms of nomological sufficiency. Basically, property X makes a difference to property Y if the occurrence of X is nomologically sufficient for the occurrence of Y. Notice the echo is the DN model's ghost haunting the halls of philosophy of mind, even if the specialists in explanation have moved on. The problem, as we've seen, is that nomological sufficiency, being part of a sufficient condition according to a law, is not the same thing as causal relevance or explanatory power. The hexed salt example screams this difference. Causal relevance, it seems, is more about contrast, what happens when the cause is present versus absent. This naturally points towards counterfactual ideas. What would have happened if the cause hadn't occurred? Yet, counterfactual accounts are often dismissed out of hand in discussions of mental causation. It's a curious disconnect. Woodward suspects this pattern. This failure to heed the lessons learned in the explanation literature might be happening in many other corners of philosophy too. Why this disconnect? Several reasons. Firstly, there's no single universally accepted successor to the DN model in the explanation literature. Secondly, applying these newer, more complex models like Salmon's causal processes or Kitcher's unificationism to specific philosophical puzzles, like mental causation involving beliefs and intentions, is often difficult to see how it would work. This leaves the DN framework, or something close to it, as the default assumption for many philosophers in other areas. The call, therefore, is for a two-way street. Explanation theorists should proactively discuss how their work impacts other fields, and philosophers working in other areas should be more willing to engage with the rich findings from the explanation literature over the past few decades. And so, our whirlwind tour through the landscape of scientific explanation comes to a close. It's clear that the quest for a perfect theory is far from over. Each model we've examined, from Hempel's deductive nomological blueprint to Salmon's causal mechanical processes, Kitcher's unificationist vision, and the challenges they face, offers valuable insights but also reveals significant gaps. Moving forward, the path seems to lie in deeper integration, tackling causation head-on, acknowledging the unique flavors of explanation across disciplines, and fostering that crucial dialogue between different areas of philosophical inquiry. The search continues.